Welcome to Scale Models. I'm Jason, your host, and I do models and electronics. Working on the traffic light project. We're going to try to break it down here for a logic-based non-MCU model. So this one may be a little daunting, and I may get a lot wrong. So I'm working through this. I worked through a little bit in my head, but I'm going to put it on paper now, and hopefully you guys can follow along. And we're going to see if we can come up with a logic circuit to do this, and then we'll do some math and things like that. So I haven't taught you guys Boolean algebra yet, so this is going to be a little bit off, but I'll get into Boolean algebra in a series upcoming. So basically, if we want to do logic, let's start with just one set of traffic lights. So we will have a red light, a yellow light, and a green light. And a green light right there. Okay. So we want to know, and we're going to write this a couple different ways, but we want to know if this light is a 1, this light needs to be off, which is a 0, and this light needs to be off, which is a 0. So if we have a logic gate and we wanted a truth table that had those outputs, so we need 3 different outputs. So we basically need a truth table. So we don't have any inputs, but what we could do is we could use the other set of traffic lights. So over here we have our red, yellow, and green for the other side of our there. So that could be our input there. So we know if we want this red on red, off yellow, off green, we know that this side green is going to be on and these are going to be off. So if we put these through a truth table, we'll write the truth table. Oh, you really can't see what I'm writing here. Hold on. Let me just switch here to a colored marker. This will work. So let's do it this way. So actually, let's make this a little more colorful. So we have red, red, yellow, yellow. Can you see that? Barely. Let me see if I can. There we go. That's a little bit better. And then we have our green here. So green. Green. And then I'll do our black for our signal. So we'll do off, 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 off. And then we'll do purple for an on signal to make this a little bit more active. So if we start and we have this side, let's say the north-south side, is going to be a logic circuit that manipulates the east-west side. So we know when this is doing something, it's going to affect this. So we have our truth table here. So let's draw our truth table. We have 3 inputs. We have a piece of copper stuck in my image. So over here we have red, yellow, yellow's not really showing up, and green. So yeah, that yellow's not really showing up. So let's try orange. It's close enough. Yeah, that shows up a little bit better. So probably zoom in a little bit on this here. And I'm going to take off this camera here. Okay, so we can see that. So we have our truth table here. So and we want to output a red, a yellow, and a green. So this is going to be our main truth table. So if we have in here, we have to put our options here. So it's 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So there's our truth table. And we want an output. So when this input is green and everything else is 0, so at 0, 0, 1, okay, we want 1, 0, 0. Okay? That's what we want. That's what we want on our output. So we're going to do some Boolean logic in a calculator to determine what gates we need. So we know that that's the output we want when this input is in there. So now, what if we want them both yellow? So if we have a yellow on, so we'll do a 1 there. We want the green off, and we want the red off. And on this side, we want the yellow on, and the green off, and the red off. So when this is 0, 1, 0, so 0, 1, 0, we want to have 0, 1, 0 over here. That's our goal for the truth table that we want. And then we need to have this light red and this light off. So, and then on when this one's red, this one is going to be on, off, off. So when we have 1, 0, 0, so 1, 0, 0 is down here, we are going to want 0, 0, 1. That's what we want. And then there's going to be a point where we want them all to be red for a little bit of time. So 1, 0, 0. And then we have 1, 0, 0. So all red. So that's going to be a little bit more difficult because if we come down to our truth table, 1, 0, 0 is already taken up by this side being green. So we're going to take a break and we're going to hold off on all red because we're going to do that with a separate bit of logic at the end. So this is our truth table here. So in any other combinations that we have here, we basically don't want anything outputted on any of these other combinations. So we need to design a circuit that basically only gives us these 3 possible combinations of inputs and these 3 combinations of outputs. So that's basically how that's going to work. So it would be so if we look at a simple problem here, if we do so we would have R naught and Y naught ended with G would give us an output. So our first problem would be R ANDed with Y, not ANDed with G. And we want that to equal R ANDed with Y, not ANDed with G, not. So we want these two statements to be equal. So if we have an AND gate and it's not, if it's, in order for an AND gate to work, you have to have a 1 on every one of them. But if we have if we have an inverter in front of the AND gate, we would have an output of R, well, we'd have an output of 0, 0, and a 1 here. So if we had a 0 input, we would have a 1, and then it would give us a 1 output on R. So that would give us a 1 output, and then we would need the same circuit to so I messed this up. So that would equal R, and then we would need another circuit to give us our second output, which would be, it would be the same problem, R naught times Y naught times G is going to equal Y naught. So we want it to be, it's going to equal a 1, and we want to invert it to make it a 0, because we want that to be a 0. And then for green, we would have R naught times Y naught times G, or ANDed with G, equals, and we want this to be a 0 too, so we'd have another, we would have a G naught, so we would have to invert it. So if we come in here and we want to draw our basic logic for this first combination, this 0, 0, 1, we would have a simple AND gate like this, an AND gate here, and then this would be R, Y, and G. And we know that we need to put these through inverters, and this one can go through, and then we would AND this like this, be an and this would be our output for R. So that would be our output for R. So there's one AND gate there. So then we would need a separate AND gate for Y. So let's draw this is our R. This is our red AND gate. So let's do another AND gate. We're just going to mess up all over this page. So we're going to come up in here and draw another. This will be our R. This will be our Y. And this will be our G, and then again, these have to go through inverters. And then we have our AND gate, and this will be our Y, and it needs to go through an inverter to give us our Y output. So that's basically that one. And this will be duplicated for the G1 also, but we'll draw it anyways. So we have our R input, our Y input, and our G input, and then we have our inverters, and then we have this AND gate. And this is going to come to an inverter, and this is going to be our G output. And this is our G AND gate. So we have 3 AND gates. Now, this can be done in a simple fashion with 3 AND gates and only one. So if you used a chip with three input AND gates and a chip with a set of inverters, you only need, since these are getting inverted every single time, you only need 1, 2, 3, 4 inverters total, and you have a chip with 6 inverters. So you would just need three input AND gates, and then you would run R and Y through an inverter into the AND gate, and G would go directly into each AND gate, and on the red, you leave it normal, but on the ground or in the green and the yellow, you're going to invert the signal. Now, since both of these are the same and they're both going to be 0, you can eliminate one of these and come off the end of this with 2 lines and get your ground or your green and your yellow light. So you can actually do away with this one, and then you could just branch this off, and then you would have 2 3 input AND gates, which is 1 chip, and then you have the inverters. So that would be basically the first stage of this right here. This would be this input and this output. So you have 3 AND gates and the inverters and all that good stuff. And then you would have to come up here and you'd have to do the same thing with the next. It would be a combination of 3 AND gates, but you don't need 3, you just need 2, because red and green are off, so red and green can share the same AND gate. They're all going to have the exact same inputs, and you're going to be inverting red and green. Red's already going through an inverter, so you just need to run green through an inverter this time. So that's another inverter. So you're looking at 1, 2, 3 inverters, and then you're going to need another one, so that's 4 inverters. So you'll have an inverter for each of your inputs, and then you'll have an inverter for 2 of your different outputs, one for green and yellow and one for red, and then you'll need another one for red and green. So that would be the basics of creating a logic system that would take what this set of lights is to this set of lights, and basically you would run a timer system to count through the number of seconds you want it before it switches on this side, and running it through the logic would switch it on this side. So the lights would be in a sequential pattern of bouncing back and forth. So this is very, very basic overview of some combinational logic, using combinational logic to run a set of traffic lights. So I am going to leave it here because I just wanted to go through creating a logic table. In the next video, I will show you how to take a large logic table of multiple AND gates, multiple inputs, and combine that all down to get a simpler object that uses less chips, and we may even find a dedicated chip that works with this system. But I'm going to try to keep this all logic based in the beginning. So this is an overview. If you guys you want to at home while you're waiting for the next video, if you want to draw up a logic system that has these 3 outputs, these 3 inputs, and inputs these codes through the different gates, draw it all out, and I will draw it all out also, and then we can compare and see how you guys did it and how I did it, because I'm sure there's different ways. And if you want to combine everything down to make it smaller, more power to you. But check that out. If you do it, you can send me an email at my social media, as my email there, and my Facebook and Twitter and Instagram. You can also visit me on Patreon. Thank you guys so much, and have a fantastic